Looks good, yeah. Can everybody hear me?
Yeah. So, and the next talk will be given by Michael Wallner on the asymptotic enumeration of large genus maps using random walks.
Thank you very much. So thank you very much for this nice introduction, and thank you very much to the organizers for giving me the opportunity to talk here today. This is joint work with Andrew L.V. Price, Wenjie Fang, and Baptiste Louf. Continue here. And I realized the paper or the extended abstract, which was accepted at FIPSAC, so I'll give a talk there as well, is not yet on archive. I take care of that later. Everyone who want to see these results, at least for the extended abstract, just give me an email, send me an email, then I can share it with you. So I have two parts of that talk. First of all, I will talk about maps. And I have to admit, I'm not like I'm not an expert on maps, so that I know that there's much more experts here. So let me give you, first of all, my point of view of maps, or what we will need. And in the second part, I talk more about where I'm more familiar with about some asymptotics. So let me start with maps. So what are maps? So here, for me, maps are a gluing of certain polygons. So you see an example here. You have here these 4 polygons. And we glue them along the edges. So this is like denoted here by these red edges. So we glue these together to form a surface. And this surface should be such that it's compact, connected, and oriented. So here you see an example of that gluing. So each of these polygons here basically is then a face in this surface here. So for example, here we always will have a root edge. This is here, this purple arrow here. And if you then follow this root edge, which is here on that gluing, basically, and keep it always on your right side, then you should see here a face with 6 edges. So basically here it would be like you go here, you keep it on the left, you go around, you go along this one, 1, 2, 3, 4, 5, and 6. And this is here basically this thing. And the genus here of a map is the genus of the surface, which is basically the number of handles or the number of holes you need here. So here we see an example of a torus. So the genus here is 1, okay? And Euler's formula relates the genus, the number of vertices, the number of edges, and the number of faces. So basically what we know that the number of vertices minus the number of edges plus the number of faces is equal to 2 minus 2g. So if you know 3 of these properties, you know that the 4th one is fixed. And the question I want to look at is, or many people looked at, is how many maps are there, okay? So counting such maps has been is like a big, it's a difficult problem, and many people have studied it. This is a non-exhaustive list, just many people have worked on that. And if I now look at A and G, let this be the number of maps with n edges and of genus G, we don't have many exact answers. One of them is like by Tutt out of from the 60s, that the number of genus zeros maps, which is basically, this is planar maps. So genus 0 means we have the surface, the underlying surface is a sphere, so no holes, no handles. So basically you see one here, then the number is given by this explicit formula here. So this is quite nice. So you see an example here, and note that I've drawn it such that I want to emphasize that there could be edges as well on the back, as on my previous picture. Here, of course, what I could do, I could move the outer face to the back and just look at it embedded in the plane, okay? Then people have looked at asymptotic answers. For fixed genus, it is known that, so we fix G, let it be 2, 3, 4, 5, that for n to infinity, oopsie, I'm spoiling my slide, the asymptotics is given, like it has this nice formula. And now the question is, of course, what happens if you send both to infinity? What happens if you send n, the number of edges, and the number of the genus to infinity? And this is a difficult question of bivariate asymptotics. There is results. I'll talk about it in a second. But is this really complicated? There is some process. Let me mention the recent progress on ACSV and analytic combinatorics in several variables. But maps do not yet fit. They don't really fit in this case, okay? And this is why we looked at this from a different point of view. And I will actually talk about a special kind of maps. So the simplest model of maps, which have just one face, okay? So from this point on, all my maps will be unicellular. So a unicellular map consists of one polygon, like here. And you glue this polygon in a certain way, same ideas. The genus is the genus of the underlying surface. And we will enumerate these guys by, as on my previous slide, by number of edges, n will always be the number of edges, and the genus G. And by Euler's formula, what we get immediately, that if I fix the number of edges and the genus, the number of vertices is fixed, okay? So the number of vertices is then given by n minus 2g plus 1, which should be positive because we have at least one vertex. So let's look again at the simplest case, genus 0. For genus 0, we're in a sphere. We just have one face. All we can have is trees, okay? Because then we have one face, which is the outer face, okay? And so basically they are enumerated by the Catalan numbers. So then guys we are hunting, I call them now En with genus 0 is just the Catalan numbers. And our goal is now to study this number. I call ENG from now on the number of unicellular maps with n edges and genus G. So, and I'm interested in what happens if n and g both go to infinity. So what is known here for this special case? Here we have a really nice result. So Hara and Zagier showed that this E and G satisfy a linear recurrence relation, which you see here with polynomial coefficients, which start with E00 is just 1. And otherwise, it's fully determined here by this recurrence relation, which I'll denote now by HZ. So you don't need to remember it. It will pop up on previous slides. But now this is what I feel much more familiar with. Now you have a recurrence relation. And now what I want to know is like, what is this ENG? What is behind this bivariate recurrence relation? Okay. So what has been done here? Unicellular maps have been studied. I don't want to say even more, but they have been studied a lot. So for genus, what is known is the asymptotics for G fixed. It is as well known for G up to a big O of n to the 1 on 3, and as well when G over n converge to a constant. So basically meaning that G is linear basically. So the genus is linear, and it has to be between 0 and 1/2 because this was from Euler's formula. We know that n minus 2g plus 1 has to be bigger than 0. Okay. What has been used before is basically the combinatorics of the problem. So for unicellular maps, there's a lot of combinatorics, okay? As you've seen, there's trees in the simplest case. And what has been done, there have been really beautiful work on bijections with other objects, such as for example, bijections of unicellular map with certain decorated trees, where you see an example here. We have a picture I borrow from Guillaume Chapuis's work, or different work where they decompose in a certain way. And what we want to do, and what I'll show you now, and what I'll talk about for the rest of the talk, is basically, I forget the combinatorics. I forget the generating functions which are behind. All I want to work on, all I want to use is the recurrence. So you just give me the recurrence relation, the bivariate recurrence relation like that. And now I want to know what is the underlying asymptotics. And this is what I will show you now, how we can get there. So what we proved is that if we let G be a sequence, which goes to infinity, well, it could be constant as well, but just like G is dependent on n, such that n minus 2g over log n goes to infinity. And recall that n minus 2g plus 1 is the number of vertices. So you can always think of this n minus 2g as basically number of vertices, okay? So number of vertices divided by log n goes to infinity, meaning that the number of vertices is bigger, much bigger than log n. Then we have this asymptotic form. We have here certain constant, a certain factor which just depends on g, n to the 2g minus 1, an exponential term n times f of g over n, I'll show in a sec what f is, and the function g over jn, where, what are they? F and j are these functions here. So they are explicitly given like these functions. So I don't read them out, but they are this is what they are. And you see plots of them here. So theta is here between 0 and 1/2, and you see f here, and here you see the function j plotted. And here there is also a function lambda. So what is this function lambda doing here? This is the last thing I have to define. And theta and lambda are coupled in a certain way. Okay, so theta and lambda. So actually, I need f, these two functions, where in terms of theta, where this lambda is another function here, but theta is defined by an implicit function equation, but implicitly that it's given by this function here, which has basically as well this nice representation as a power series. Okay, so basically you would need to invert this in order to get it. It's completely doable, and here you see the function here. But this parameterization allows to have this simple form. And it looks really complex. You don't need to remember any of this, okay? But the goal is to have it not in some certain regime, but you have it like in really in a very, very big regime. So basically always when the number of vertices is much bigger than log n, then you have this. And this formula simplifies to the special cases. So if you look at it and you compute, for example, G fixed, what's going to happen, then the asymptotics of this formula gives you exactly the asymptotics formula which have been already derived. Okay. Okay. So this is maybe the most I know it's a very technical result, but it includes like a big regime. Okay. And now I want to show you how we got there, how we get that. So the idea here is, as I said before, we don't want to work with the combinatorics. We really, it's actually we just work with the recurrence relation. All I use is the recurrence relation, and here I will need another ingredient, random walks, and that's why we termed this like the random walk method. And this will not be limited to these kind of recurrences. So basically, it's basically more like a proof of concept that what this method can do. So, okay, here the recurrence relation, okay? So the recurrence relation from before, I called it HZ. Now the basic idea, it's really like this is just the start, this is the start of it. We use, of course, the recursive nature of the problem, okay? So really basics, like if you would be able to guess an explicit formula omega ng, something like this, how would we be able to prove it? Well, if this function, we would need to show that omega ng satisfies my recurrence and the initial condition, which is just 0, 0, is the same as E0, 0, which would be just 1, then of course they are the same, right? But this is here, of course, not possible. Right? It's a bit too complicated. So that's why we want to look at it asymptotically. And the idea is now, our goal is to find an explicit asymptotic formula for omega ng such that it satisfies the recurrence relation asymptotically. So basically this means that it's the same recurrence relation you see here. It's really the same, but instead of an equality, and I will make this explicit, this is approximately the same. And the idea now will be to show you how to make these approximations rigorous, how to make equalities out of this. And then if we additionally have that it's not only the recurrence relation, but it's asymptotically equivalent for large n at least at the beginning, then hopefully we can transfer this asymptotic equality to the full range. So this is really the idea. But of course, I mean, there's a lot of hand waving here, okay? This is just an approximation, but I want to do it for asymptotically for really large n. This is the first idea. And what I need now to do is basically to explain a little bit how these approximations here can be made into equalities, basically, how we can capture here the errors. And there's like two things. So first of all, of course, you would ask like, okay, here's the word like, if you would find or if you would guess an explicit solution. So where do we get it from? Yeah, I could just tell you we got it, right? But I will show you, I want to at least convince you that there is like a systematic way of doing this. So let me answer this first. So how do you get an explicit asymptotic formula? What do you do? Well, you use the recurrence, obviously. So the first thing we did, it's a linear recurrence, so you can compute numbers, right? So first of all, you plug it into your computer and you compute many numbers for E and G. I just rewrote it such that we have here E and G on the left and here some factor and these two terms, and we compute like all the big table for the first 1,000 terms. And then what we do, we look at quotients. So this is nothing new. There is many tools, and I just want to mention one paper here. Oops, I have to go back, by Tony Goodman, and there's many references in there about what you can do. But basically, what you look at now, you plot many things. Okay, you look at many subsequences, and you look at quotients because they are much more stable, and you hope that they show some. We want to understand the growth of these objects. You know, so for example. let's fix an integer k, and we look at how does the quotient ekg over g minus 1 over ekg over g grow. Basically, you look at the recurrence along this line, along one ray, so 2gg, 3gg, 4gg, and so on, and look at how does it grow, okay? And what you see, what you conjecture, basically, it grows like g squared. And you can make this a bit more explicit. I show it here for 3gg, it grows like this, where you can as well make quite good guesses on these constants here, okay? Gives you already like some clues what's going to happen. Then you look at other quotients as well, okay? So for example, you fix theta as like g over n, so which is like this quotient, the relation between genus and the linear case in the genus. And you look at the similar quotient, where here we now look at the subsequence en theta n. So we look at this quotient here. Again, the first one was maybe you can think of at the upper boundary, and the other one is in the lower boundary. So you look at some rays, and you see like, okay, it seems to converge to something. It depends always on my feeder. And after playing a little bit more, and here it's a lot of trial and error. So here you have to be a bit lucky and find something. But we guess that it has more or less this shape. So E and G behaves asymptotically, hopefully, like n to the 2g minus 1. So some exponential growth, e to the n times depending on some function, which depends on the quotient, times another function. And this is still just a guess, but we use this as an ansatz, okay? So I use this now. Let's assume it's this. Let's hope that that works out. And what do we do now? Well, we still need to determine f and j if that works, but now let's put our guess into our recurrence, because that's what we have. And if you plug that in, what you do then, you look at, again, at some asymptotics of these objects. For example, you fix g to be theta of n and let n go to infinity, and look at the asymptotics of this first order asymptotics and see what's happened. And for example, if this guess has to hold, then basically what you get is a certain differential equation here for f. So you see 1 should be equal to 4 over e to the minus 2, blah, 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 and so on, okay? And what is quite nice, this is solvable. So you play with it, you parameterize it in a certain way, and this was where the function, where on my in the main result, the theta and lambda and f and j are coming from, basically. This is then solvable. This is a solvable differential equation, and this determines f, and then gives you this these results. Okay, but this is all I want to say about guessing. Okay, so we have this now somehow, but there's a lot of work hidden here. And now what we do? Well, of course, we have to prove our guess. So what we do, we look again at quotients. And to make it a bit less technical, I just write A and G for some weights here. This is my recurrence again, and B and G for the other weights. This was where certain rational functions on it. Basically, they just depended on n, but I keep it as n and g. And what we do now, okay, we have a guess now. So let's divide by it. Again, quotients. But now we divide E and G by omega and G. Okay, so I just divide my full recurrence by omega and G. And what is my idea? Basically, I want to look at now at this quotient Q and G, this object here, which is my guy I want to prove E and G, and my omega and G. And you have to think of this omega is explicit. This was our guess. It's explicit. It's the function I've shown you. It's maybe not the most simplest one, but it's completely explicit. And then I rewrite this in such a way that I have now a recurrence relation for Q. Q and G is a function here, A and G, my weight from before, a certain weight, omega, explicit. Complicated, but explicit. And Qn minus 1 to G, and so on, another thing here. And let me simplify this. So what we get is this recurrence. Alpha and beta are now basically, they're exactly these weights. I just repeated. And what we want to prove now is for this recurrence that the quotient is 1. Because then, if the quotient is asymptotically 1, then E and G is asymptotically Q and G. Okay, so we have the same recurrence, but with new weight. It's not the same, but the weights change, but the shape is basically the same. And now we kind of like, in a sense, we try to, with our guess, we try to simplify the problem and hope that the guess will now lead me somewhere where I can solve maybe make the recurrence a bit more complicated, but the result a bit simpler. So what I'm hunting now for is that I want to prove that Q and G is asymptotically everywhere 1. And these weights, alpha and beta, they're explicit, completely explicit, okay? And now the random walks come in. Because I want to prove that something, which is always positive, is asymptotically 1, okay? But this like screams like probabilities or something like this, okay? And what I want to do now with this recurrence, I can of course interpret as well as a walk, as a random, or first just as a weighted walk. So let me show you the domain of this walk. So this is the recurrence. And if we have here in gray, you see here this cone, this triangular cone here, which is basically the domain n is bigger than 2g. So here we can only live here, basically in that cone. It cannot leave this cone to the left or below. And the steps we could do if we start at ng, we could go to the left. This is qn minus 1g. And we could go like down like this with a step -2, -1, okay? So this is the first step. And then we have weights here as well. And then we can, of course, iterate. So we just use the recurrence again, and the weight that we get here, the weights here become products, but we get here this. So what happens? We do one more step in this direction from this point and one more step here. We reach these 2 points. We go one step here and one step here from these points. And after 2 steps, we reach this point. And now we can go on, of course. Like this is very classical. So we have here in the next step, we reach this point. In the next step, we reach this, this, and so on. And at the very end, we have to reach 0, 0. This is how it's designed. It cannot leave the cone, it has to stay in there. And at the end of the day, the recurrence here tells me that Qnj is nothing else than the sum over all paths from ng with these steps, so in this lattice, to 0, 0, or where, of course, we have to be careful of the weights. And here it's important that Q00 is 1, but we can rescale everything, okay? So here we have now an interpretation in terms of walks. And now the idea is, what if this is really basically a random walk in the sense that alpha and beta are probabilities, okay? So they're positive, that's fine. This is how we designed it. But what does that mean? So assume that the alpha and beta at each step sum up to 1, okay? So at each step, for example, beginning with a certain probability goes here, with a certain probability goes here. And this is a random walk. And then Qnj is nothing else than the probability that if we start at ng, we end at 0, 0. Well, of course we do this, if it would be really probabilities, because that's what it has to do. And this is, of course, the case in that case. But what our goal is now to show is if we could find omega ng, so we still have some freedom, such that they're approximately probabilities, then we could maybe use this idea. And it turns out that's possible. So what you can do, this is just from before. I just copied everything is explicit. I just want to show here that everything is explicit. And we add just one more term. So you remember maybe that, this term, e, an exponential term, and this term. And here you see another factor. And this factor I need in order to be able to show this result. And this is kind of like one of the things when I mentioned at the beginning, I want to make approximations rigorous equalities. What does that mean? The sum here is equal to 1 plus a big O of 1 over n log n squared. So here it's now really an equality with an explicit error term. And the key here for everything for us to work, and this is actually why we needed to add this term, is that this term here is summable. And this is coming from the log n squared, okay? So, and this thing here looks quite innocent, but that's the key result here to make everything work. And this is like, everything is completely explicit. So how do you prove it? You just, what I've shown you, you could do it now. You know, I wouldn't do it on a piece of paper. It's a lot of, it's quite technical. Well, at least I need like 8 to 10 pages to do this and have several cases. But basically, F is explicit, J is explicit, omega is explicit, everything is explicit. Just do it, okay? You show that. It's really that's what it is. But this basically is now the intuition, it will work. The interpolation by random walks will work. And this is the last step. This is the last step now I have to do. This is still an approximation. Now let's define an approximating real random walk with our new insights. So, okay, we have that lattice. And I just define our random walk with the same steps. So we can go left, or we can do a step -2, -1. And which probabilities do I choose? I either choose alpha divided by alpha over beta, or beta over divided by alpha over beta in its steps. Now it's really summing to 1. Exactly, summing to 1. This is not the same walk. It makes the same, does doing the same steps, but I changed this, the weights again. But this is now a random walk, which is hopefully close. And the key is, it is close because alpha plus beta is close to 1. And it's summable. And what is then the key here, and I won't prove this, is that a certain quantity is conserved. And what happens? I show it here. After one step, the expectation of Q evaluated at my new position, or my new position of my random walk. So my Q, you can think of now, I plug in the values of this new, that's like a functional of this. I want to couple now the random walk with the Q I want to prove with this, with the Q coming from this recurrence. The expectation of my Q is after one step more or less the same, meaning the expectation here is the same as in this bubble, and in this bubble it's the same as in this bubble, and in this bubble it's the same in this bubble. So basically from the beginning it's the same until the very end. Okay, and here I don't make this rigorous anymore. It's too much technicalities anyway, but we can make this one as well rigorous. The idea being you can here really use as well the random walk. And at the very end, what we show is we stop the random walk once it hits one axis, and we show that basically with high probability it hits actually this axis, and this is good because this is the axis where the genus is 0, where we control it, because there we have trees. Okay, this is where we have full control. We can show that the random walk in omega in this domain with high probability it hits this axis, and that's everything we needed. So we can now show, because here we know that Q goes to 0, we know it, Q and 0 converges to 1. And here basically we have this asymptotic initial condition. Let me just quickly show it because I know I'm out of time basically. But because of this, now we know that QNG is basically Q evaluated at the beginning of the random walk. By the conserved property I've shown you, this is the same as the expectation when it stops. So basically on one of these axes. But we know with high probability it will hit this axis where this holds, where it's 1. And this is the key to show everything just from the recurrence relation, okay? So let me wrap it up. Our idea was to approximate a linear recurrence relation by some random walk. And let me show we didn't use the combinatorics, except we used here basically, we needed some guesses, but we didn't use the generating function or anything from the combinatorics of the underlying problem. The method also works for the other range, and it will, but it's technical enough, and basically the shape changes a little bit. So there's a phase transition happening at log n. And what I want to emphasize is the method is robust in the sense that we can change the recurrence a little bit and it will still work. The generating function would, if there is one, would disappear. And here there is actually a generating function, which is nice for these unicellular cases. But if we change it a little bit, method is still possible. And what we're working on right now is extensions to other recurrences, other coefficients, different steps, different weights, and so on. So that's it. Thank you very much. And I'm happy to answer any questions.
Yes.